Carl, we're supposed to cover 13.8 billion years in this video series, right? Well, in this video, we're only covering the first 10 billionth of a second. Just feels like the pacing is off. Hi, welcome to episode 2 of Living as Nature, Forces of the Universe. Use the Force, Luke. I don't know who that was. I don't know. Today, we're going to talk about the beginning of our universe. Well, we're going to talk about pretty darn close to the beginning of our universe. Our goal is to focus on how the earliest moments of our universe, in particular the very first second of its existence, provides a necessary foundation for the rest of the story. The stories of elements, stars, galaxies, planets, and all other living creatures, including us, and also Carl. What? You're built different. It's a compliment. We should start by noting two things. First, no one knows what was going on before our universe showed up, or if it even makes sense to talk about a before, since time as we know it seemed to start with our universe, as part of space-time. I'm just saying, Carl, land before time made no sense. If there's no time, there's no space. How can you have a land before time? Yeah, fine, I'll write my senator again. A famous theologian, Augustine, once wrote about the question, what was God doing before God created the world? Augustine wrote, somewhat grumpily, that he'd avoid giving the answer that God was creating hell for people who asked stupid questions. He was probably an awesome teacher. But that's not our position here. We like questions. And it's a good question. What was there before our universe? But the truth seems to be, as far as I can tell, we just don't know. Maybe the universe is eternal. Maybe it's part of a multiverse structure. Maybe it formed from a previous black hole. Maybe some intelligent creator made it. All these options seem absurd, but something has to be true. Second, there's disagreement about how far back we can confidently trace the universe's development. Two major theories seem to dominate the field. The first theory is the standard Big Bang theory. I'm not going to do it, Carl. I'm not going to sing the theme song. It all started with the Big Bang. Damn it, Carl! According to this theory, at t equals 0, which means time equals 0, referring to the beginning of time itself, all the energy of the entire universe was packed into a singularity, or an infinitely small, hot, and dense point. Infinitely dense. Who does that make me think of? Yeah, I'm looking at you, Carl. It then erupted, hence Big Bang, kicking things off. We can't say much, if anything, about what happened right after t equals 0. So the traditional Big Bang theory starts at t equals 10 to the negative 43 second. That's a very small fraction of a second. Written out, it looks like this. Spoken out, it's 10 millionth of a billionth of a billionth of a billionth of a billionth of a second. Billionth. Word has lost all meaning. To try to make sense of just how small that number is, if you were to take that fraction of the distance between the Earth and the Sun, roughly 94 million miles, you would be less than 1/trillionth of a trillionth of the width of human hair away from the Earth. It's so small, it's almost equal to the attention span of the average teenager. Which is actually larger than my attention span, so shout out to you teenagers out there. If you want to know who arrived at that number, and how, check out the links in the description for this video. The short of it is, a scientist named Maxwell Planck, using values for the force of gravity, the speed of light, and the ratio of a photon's energy to its frequency, yeah, Carl, I know what I just said. Kind of. Did some fancy maths, and came up with a specific mass value, Planck mass, a specific distance value, Planck length, and a specific temporal value. You guessed it, Planck time. And apparently he named stuff like Walt Disney named stuff. Actually, I think they were named after him, so he gets a pass. There are actually two different values for Planck time, but the one we use most commonly is 1.35 times 10 to the negative 43 second. Why this number was important didn't become obvious until later, when scientists argued that this time interval represented when what we call the four fundamental forces separated from one another to become separate forces. The four fundamental forces are gravity, electromagnetism, strong nuclear force, and weak nuclear force. Carl, I feel like people got bored naming after they named the first two. The last two kind of feel phoned in to me. Each of these forces play a separate and crucial role in our universe. More on that later. The claim is that, during the Planck era, or epoch, the first 1.35 times 10 to the negative 43 second, there was a single unified force, and the laws of traditional physics didn't apply. Like most male politicians, when it comes to the female reproductive system, scientists just don't know what was going on there. At 1.35 times 10 to the negative 43 second, we enter what this theory refers to as the Grand Unification Epoch, where gravity splits from the unified force, but the other three remain unified. Why did this happen? I don't know. I suspect Yoko Ono had something to do with it, Carl, but I'm not a scientist, so I can't say. This period lasts till 10 to the negative 36 seconds, so not very long. But during this period, we begin to see the production of the first elementary particles, quarks and gluons. We'll say more about particles in the next video. That's one theory. Another theory is that we actually can't go back beyond 10 to the negative 36 second. This theory is at least one form of the inflation theory, and it suggests that the universe may not have started off as a singularity at all, or at least the data can't prove that it did. The universe was really small at 10 to the negative 36 second, and something triggered it to undergo a series of extremely rapid and intense inflations. According to this theory, this inflationary period set up the conditions for the Big Bang to occur. In other words, first the universe inflated, and then the Big Bang happened. Before inflation occurred, we just don't know. For more details on these two theories, see the links provided in the description for this video. Interestingly enough, if you go onto NASA's website, you can find an article supporting inflation theory, suggesting that inflation occurred prior to the Big Bang. But you can also find a graphic depicting the Big Bang occurring before inflation. Fun times! Regardless of which model we accept, there's a lot of common ground between the two. Both models, for instance, have a Big Bang that occurs. This is because there's such strong evidence for a Big Bang occurring that it's hard to argue otherwise. This includes the data that our universe is expanding, which was first discovered by Edwin Hubble. The strongest piece of evidence was the discovery of the cosmic microwave background radiation, CMBR, which is an echo of the Big Bang that had been predicted by American cosmologist Ralph Alpherin in 1948. It was found, by accident, in 1964 by physicists Arno Penzias and Robert Wilson in New Jersey. Also, Big Bang models today incorporate inflation, maintaining that at 10 to the negative 36 second, the strong nuclear force tired of the party and left the unified force as well. In the more traditional Big Bang model, this event triggered the inflation period. But note that in this model, inflation occurs after the Big Bang, not before it. During this inflation event, in a tiny fraction of a second, the universe expanded by a factor of 10 to the 26th, or this number. I expanded like that once, Carl, when I visited an all-you-can-eat buffet. It was not enjoyable. Over the next fraction of a second, the electromagnetic force and the weak nuclear force both decide that they too would like to try their hand at a solo career. And by 10 to the negative 10 second, or 1/10,000,000th of a second after t equals 0, we have our four separate fundamental forces. Yay! Let's take a moment to consider why these four forces are important. Each one has a particular role and strength that, in relation to the others, establishes a structure to the universe that allows complexity to develop. Gravity functions to attract objects with mass together because objects with mass bend space-time. Shout out to Einstein's theory of relativity. The strength of gravity increases as objects get closer together and exponentially decreases as they get further apart. Gravity is what's responsible for keeping our planet in orbit around the sun and keeping us on our planet. It's also the reason I can't dunk a basketball. Yes, Carl, that coupled with my extreme lack of skill. Thank you. Electromagnetism is based on electrical charge, that is, positive or negative, not mass. When two objects have the same charge, they repel one another. When they have opposite charges, they attract one another. Large objects often end up canceling each other's charges out, leading to a neutral effect. So electromagnetism tends to do a lot of its work at smaller levels. And at these levels, electromagnetism can overcome the force of gravity, allowing things to come together that might otherwise drift apart. For instance, without electromagnetism, atoms, which contain both protons, which have a positive charge in their nucleus, and electrons, which have a negative charge orbiting around their nucleus, wouldn't be able to form. And without atoms, we don't have molecules, we don't have stars, we don't have galaxies, and we don't have life. The weak and strong nuclear forces don't have an obvious effect on us. Unlike gravity and electromagnetism, we can't see their effects in everyday life. But they're still essential for the structure of the universe as we know it. The strong nuclear force can hold very small things together that have the same charge. It's super strong, hence the name, but its power over the other forces is limited to the subatomic level. So, if there is more than one proton in the nucleus of an atom, you can tell this by the atomic number of the element, which simply measures the number of protons in the nucleus. The strong nuclear force is at work holding these protons and the neutrons together. So, without the strong nuclear force, you don't get the other elements of the periodic table. And you're left with a rather bland universe in terms of complexity. The strong nuclear force also works at an even smaller level. Atoms are made up of subatomic particles, protons, neutrons, and electrons. Protons and neutrons are made up of elementary particles called quarks. And the strong nuclear force holds together the quarks that make up protons and neutrons. So again, no strong nuclear force, no protons or neutrons. No protons or neutrons, no atoms. No atoms, no molecules. And, well, you get it. The weak nuclear force also works at the subatomic level, but in a different way. The quarks that make up protons and neutrons can either be up quarks or down quarks. Man, Carl, weak and strong, up and down. Someone was on a creative rampage when they named these things. The weak nuclear force can change quarks between up and down variations. Doing so transforms protons to neutrons, and vice versa, in a process called beta decay. This process actually changes the makeup of the atoms, because when you change the number of protons in the nucleus of an atom, you change the atomic number of that atom, and now it's a different element. For example, carbon-14 becomes nitrogen-14. The weak nuclear force is also necessary for both nuclear fission and nuclear fusion. And without nuclear fusion occurring in stars, you don't get heavier elements. And, you guessed it, you don't get a universe like ours. Now, it isn't just that these forces exist. It's that they exist with very particular values in relation to one another. Take gravity, for example. Sir Isaac Newton went to great lengths to calculate the constant force of gravity to be G equals 0.000000000667, with the units being notated as follows. That is a weird-ass number, Carl. Yes, I know he was much smarter than I am, but still. That's a weird number. But it's interesting to note that if the value of G had been slightly higher or slightly lower in relation to the value of electromagnetism, you just wouldn't have a universe like ours. The universe would either collapse back in on itself or expand so quickly you wouldn't get the kind of complexity that we see. Other values are similarly just within the right range to allow complexity and life to form in our universe. Some people who believe in a creator God, and a number of them scientists, have argued that these small margins are evidence that the universe has been finely tuned by an intelligent designer, i.e., God. And indeed, it seems like the rather astronomical, unlikely odds that these numbers would be exactly what they are, if there is only one universe, does raise the question, how did this happen? Some scientists, however, such as the British astronomer Martin Rees, argue that we live in a multiverse of infinite universes, and so it was inevitable that one of these universes would have these values to permit complexity in life. So, no surprise that it happened. Other scientists are content to acknowledge that our universe simply had the Goldilocks conditions to make complexity and life possible. Goldilocks here, of course, referring to not too much, not too little, but just right. And they say we simply can't know why this is the case. We'll revisit the idea of Goldilocks conditions in later videos. These four fundamental forces are really just the tip of the iceberg. We could discuss more about other universal constants, the laws of thermodynamics and motion, which we'll touch upon in future videos, and dark matter and dark energy. But for now, hopefully you have some idea and some appreciation how the first 10 billionth of a second of our universe shaped the story of the rest of the universe so that stories like ours are possible. In our next video, we'll discuss the formation of subatomic and atomic particles, as well as stars, galaxies, and heavier elements. So it'll cover more than 10 billionth of a second. Until then, farewell. And it all started with, we don't know, maybe an inflation that led to a big bang, or big bang that led to an inflation. It just doesn't work as a song.